All right, all right, all right. Who's ready for some more math? I hope the answer's you. Last section we solved equations. Now we're going to solve inequalities. Think about what inequalities are. They are like equations, except for they have an inequality symbol, maybe a less than symbol, or a greater than symbol, or maybe even less than or equal to, greater than or equal to, even not equal to. Those are all inequality symbols, symbols other than equal signs. So everybody's buying the caramel apple suckers right now. So what do you think is better, the red or the green? So is the red sucker less than the green, meaning the green is better? Or is the red greater than the green? I think most of you guys seem to think that the green are better. That, that seems to be the consensus. So we would say that the red sucker is less than the green sucker, or you could, let's see if I can get this trick to work, flip it around and read it the other way, and we could say that the green sucker is greater than the red sucker. So let me show you that again. You can just flip it. Notice that when you switch what's on the left side to the right side, what's happening to your inequality symbol? Show you one more time. Your inequality symbol flips around as well. That's going to be an important key when we start solving these inequalities. So here we go. First of all, let's talk about solution sets. What's the solution set to these inequalities? Express the solution graphically and in set notation. So two different ways they want us to write it. Again, we're going to solve these very similarly to the way we solve equations. There's going to be one difference, and I will tell you what that is when we get to it. So you still want to get your variable by itself. Your variable here is that q, and we want to undo the order of operations, so we want to subtract the 10 off first. We are left with then 5q is greater than 10. And then to finish getting q by itself, because it's 5 times q, we undo the times, we divide. Q is greater than 2. Well, how many numbers are actually greater than 2? What could q actually be? It could be 3. 3 is greater than 2. So is 4. So is 5, 6, 7, 8, 9, 10. You could keep counting forever and ever and ever. In addition to that, you also have numbers like 2.1, 2.2, 2.3, 2.4. 2 1/2, 2 3/4. So you have a lot of decimals and fractions also. So because you have an infinite number of solutions to this problem, we like to write them, the solution using a graph. So you make your number line graph, place just the number that comes up in your inequality is the only number you really need. So we have our 2. Something some of you guys were missing in the previous section, 2.1, if you have less than or greater than, and you are graphing, on your number line, you would graph that with an open circle. That means you don't include the number it's on in your solution. So like for this problem, we use 2 because that's the number in our solution, but we don't want to include 2. 2 is not greater than 2. So if we plugged exactly 2 in, we get a false statement. So 2 cannot be a solution. But every number greater than 2, even if it's just the tiniest little bit greater than 2, like 2.00000000001, that is greater than 2, so that would fit. So anything past 2, anything greater than 2 at all, would be a solution. Okay? Now, if it had an equal to underneath it, then we would use a closed in dot, and we would say we are including the number that it's on. Okay? So example 2, you would have to use a closed dot, because whatever we get for our solution, we're going to be also equal to it. Okay, finishing up number 1, though, we want to use set notation. For set notation, we use these nice curly brackets. And make sure you're using the variables that they say. That's something else I've noticed you guys doing. A problem will tell you to use p and you still use x. So you want to use whatever variable is worked out in the problem or is given in the problem. Okay, so we say Q is real because we're always working with real numbers. So you're writing that every time. Vertical bar. And then how are you describing your set? Well, we're saying that Q has to be greater than 2. So it's really the normal solution you would give, just written in this fancy brackets and specifying that Q is real. Okay. If your answer were just a single number, like maybe if you solved an equation and you got Q is exactly 4, when you write that in set notation, you don't have to specify anything. All you have to specify is your solution. So it's nice when it's just one number, you just stick it in there. Even if it's just 2 numbers, you just stick them in there. But when it's an infinite amount of numbers, you have to describe the set in set notation. All right, number 2. First thing you want to do is distribute. Simplify your left side by distributive property. Now simplify your right side with distributive property. Each side is now completely simplified. So we have variables on both sides. We want to get those together. So we subtract 2x. That gives us 2x minus 12 less than or equal to negative 4. Looking at your x value, get rid of the numbers that are on the same side as it. Choosing to add 12 first to get rid of the minus 12. 2x is less than or equal to 8. And then divide by 2 to get x all by itself. X is less than or equal to 4. Okay, so set notation. X is real. X is less than or equal to 4. So again, if you have an infinite amount of solutions or too many solutions to list out, you're going to use the description in the set notation. For your graph, we need a number line with a 4 labeled on it. Closed dot, because we want to include 4. We could be exactly equal to 4. And then where are your numbers less than 4? They're to the left. Okay. Find the solution set, graph it, and check your answer. 3x minus 4 is less than 8. So you guys go ahead and do this one, see how it goes, pause the video now and work it out. Okay, check it out, see what you got, see if it's the same thing as what I got, and then make sure you use set notation correctly and you graphed it correctly. Make sure you have your shading of your answers going the correct direction. Will performing the following operations change the solution set? Okay, so it's the same problem we just worked on. We know our answer from when we did it by normal, how we would choose to do it. We got x is less than 4. So we want to see, does this answer change when we do it these 2 different ways? So the first thing they've asked us to do is start by adding 10 to both sides. You might say there's no 10 in that problem. That's okay. They're simply asking us if we changed it to this problem, if we start by adding 10 on both sides, will it change our answer? Okay, so to check that out, you're going to combine negative 4 plus 10 and 8 and 10. Then continue solving by subtracting 6. And then divide by 3. And check it out, we got x is less than 4. So what that tells us is the addition property of equality can translate and become the addition property of inequalities. We can still add any number we want on both sides and get the same answer. Likewise, subtractive property also works for inequalities. Okay, the second one, start by multiplying by negative 2 to both sides, solve, graph, and check. We didn't graph that, but it's the same answer as the last graph. Okay, so this one, we want to start by multiplying by negative 2. Be careful when you do that. You would have to multiply the entire left side by it. So you would want to do distributive property. And when you do it on the right side, make sure you include that you're multiplying so you don't end up thinking you're subtracting. So we get negative 6x plus 8 is less than negative 16. Okay, so this is our new inequality to work with. So solve that one. We would subtract 8. Negative 6x is less than negative 24. Divide both sides by negative 6. And x is less than 4. Same answer. Okay. Let's check these. Let's check them into the new equations we created, which would be, or inequalities, right here and right here. So if we're saying x is less than 4, we could pick any number less than 4 and it should work. Let's pick 0. 0 is always easy to check. So over here I'd have 3 times 0 plus 6 is less than 18. I'm just plugging into the start inequality. 3 times 0 is 0. 0 plus 6 is 6. And 6 is less than 18. So yep, sure enough, we're good there. Over here, let's plug 0 into this start inequality, the green one now. Negative 6 times 0 plus 8 is less than negative 16. Negative 6 times 0 is 0. 0 plus 8 is 8. 8 is less than negative 16. Ruh-roh. That is not true. 8 is not less than negative 16. Absolutely not. So what that's telling us is we've got something wrong here. When we chose to start by multiplying by negative 2, it changed our problem. Here is why. So for inequalities, we already said we can use the addition property of inequalities. When we used it over here, we had no problems. Our answer checked out. And what that's saying is if you have an inequality, you can add the same thing on both sides. You still have the same statement. You can also use the multiplication property of inequalities, but there's a stipulation. Only when the number you're multiplying by is greater than 0. So if you have an inequality and you want to multiply both sides of it by something, whatever you're choosing to multiply by, it must be positive. It has to be greater than 0. Pause the video, write that down. Okay, example 4, solve using only properties allowed for inequalities. So we can use addition property and subtraction property as well, because subtraction is really just a different form of addition. And we can use multiplication property, but only if we're multiplying by a positive. So how could we solve this inequality? Negative h is less than negative 7. So your first thought would probably be you're either going to multiply by a negative or divide by a negative to get rid of that negative sign on the h. But from back here, remember, you're not allowed to multiply or divide when c is negative, when your number that you're choosing to multiply or divide by is negative. So instead, how else could we get h positive? Well, we could add it on the other side. Negative h plus h, then that would cancel, and if everything cancels, you'd have a 0. We get 0 is less than negative 7 plus h, not like terms, so we don't combine them. And then we would add 7 on the other side. We get 7 is less than h. Okay, sometimes we don't like when that variable comes last, so we can rewrite it with the variable coming first. Now, because the inequality symbol here is open, the bigger open side is open to the h, you want to keep it that way. So essentially, whenever you flip the order your things come in, so whenever you move the back element to the front and the front one to the back, you also need to move your sign. You want to flip your sign. When you flip the order, you need to flip the sign around as well. Okay, so we get h is greater than 7. In set notation, we would have h is real, and then h is greater than 7. Okay, so this is all well and good. We can solve like this every single time, or we can take a shortcut. The shortcut is, if you want to multiply or divide by a negative number, you may. But what you also have to do is flip your inequality sign. Write that down. Super important. This is your big difference between solving equations and solving inequalities. If you want to multiply or divide by a negative number, you may, but you must flip your inequality sign. So let me show you that on this inequality. So we know negative h is really negative 1h. So what we could do is we could divide by negative 1. Because you are dividing by a negative number, your less than sign flips around and becomes a greater than sign. And we get h and we get 7. And take a look at that. It's the same thing we got over here. Okay, so that's why you're doing this, because you really could solve it using these other steps where you add that variable to get it on the other side, but then it's on the other side of your inequality symbol. So if you're taking the shortcut, you would just need to flip it around. Going back to here, I can show you just for a minute why that happens. Say we have 2 is greater than, well, let me use a different number. Let's say 4 is greater than 2, which I hope you would agree is a true statement. If I multiply that by a positive number, let me pick 3. 3 times 4 is the same as 2 times 3, right? You would have the same inequality symbol. 3 times 4 is 12, which is greater than 6. So I took my original inequality, I multiplied by 3 on both sides, and I still have a true inequality. Starting with that same 4 is greater than 2, if we multiply it by negative 3 on both sides, then I get this statement, negative 12 is greater than negative 6. But negative 12 is not greater than negative 6. So when I multiply by a negative, I would actually need to flip my sign around and get negative 12 is less than negative 6. Okay, so as soon as you multiply by that negative sign, take your sign and flip it. All right, number 5. So here is your given problem. The first thing I would do to simplify it is distribute this negative 3. Negative 3 times 2x is negative 6x. Negative 3 times 4 is negative 12. And I still have the negative 20 over here. I don't need to flip my sign. Yes, I multiplied by a negative here, but I didn't introduce that to the problem. I didn't change the problem in any way. I'm simply simplifying what they've given me. Okay, so we're all well and good there. Then you would need to add 12 to both sides. Negative 6x comes down. My inequality symbol stays the same. All I did was add a number. And negative 8 here. Last step, I need to divide by negative 6. And at this point here, I have divided by a negative. I introduced that into the problem. I chose to divide by a negative number, so my inequality symbol now has to flip around. And we get x is less than 4/3. That means any number less than 4/3 should work. So if I have 4/3 here, I know that, let's say 0 is less than 4/3. So I could try 0 and see if it works. 2 times 0 is 0, plus 4 is 4, times negative 3 would be negative 12. Is negative 12 greater than negative 20? Yes, it is. So that is correct. Okay, number 6, we have a not equal to sign. You're still going to solve it just like you would solve any other equation or inequality. Subtract 10. We get negative 20 is not equal to 4x. So I'm just bringing that sign down. Then I'm going to divide by 4. and I get that -5 is not equal to x. Or in other words, x is not equal to -5. So that means any other number would work out for me here besides -5. Okay, in set notation, we say x is real, x is not equal to -5. I don't like the way I just said that. It's not saying that every other number would work. It's saying that x is not equal to -5. So that's what you were trying to solve. You were trying to figure out what x was not equal to. Okay, so we have figured out x is not equal to -5. Hopefully I didn't confuse you on that. Okay, you try. Pause the video. Don't keep watching it. You need to pause it. You need to try it on your own. You need to see what mistakes you might be making, or if you've got it completely correct and you're good to go. Pause the video. Try these next two examples. Okay, check your work. On A, problem A, I subtracted 6, then I divided by -2. Because I divided by a negative number in this step, I switched my sign from here to here. I got v is greater than or equal to 13. Part B, I subtracted 6x, and then I subtracted 4. I did not ever multiply or divide by a negative, so my sign never flipped. It always stayed less than. Also, be careful that you don't accidentally go back to an equal sign just because you've been working with equations. Make sure you're always bringing down the inequality. -9 is less than x. A lot of times we don't like reading them that way. We want the x to come first. That's totally fine. Just make sure when you switch the order, you also switch your sign around because you're reading it backwards. Okay? And finally, I'll leave you with another quote. It's not that I'm so smart, it's just that I stay with problems longer. A lot of times in math, we think the good math students are the ones who can compute the quickest in their heads, the ones that can tell me what 25 times 14 is, mental math the quickest. But that's not really what makes someone good at math. That makes you a good calculator, which is a skill to be admired, but it doesn't make you good at math. What makes you good at math is being persistent. Read my green poster up at the front of the room. One of my college professors said that, and it kind of really stuck with me. You've got to persevere in math. You've got to be persistent. You've got to not get frustrated when you're not getting things right away. That's all right. It's okay not to pick everything up the second you see something. Okay, you just have to be willing to stay with that problem a little bit longer. All right, keep working on your packet. Good luck on your mastery check.